So hi everyone, today I'm going to be talking to you about unmasking the Godfather. Together we're going to be reverse engineering the latest Android banking Trojan. So who am I? I'm Laurie Kirk. I'm a reverse engineer at Microsoft. I specialize in cross-platform malware analysis with a focus on mobile threats. I also run a YouTube channel called Laurie Wired where I talk about a ton of different mobile reverse engineering and a lot of different programming techniques. And today I will be representing myself as a security researcher, not representing Microsoft. So if you would like to follow along, I have a QR code. I promise it's not linking to malware for this one. And you can go ahead and scan it and go to my GitHub, and this contains all of the supporting materials for this talk, as well as the SHA-256 hash of the malware that we're going to be analyzing today. All right, so I think let's get right into it. So this application that is promising to protect you, it's saying it is the legitimate Google Protect application, is actually a banking Trojan, and it's going to go ahead and steal all of your data and drain all of the funds from your bank account if you install this on your device. Now, I don't know about you, but I don't really expect Google Protect to need to make phone calls on my behalf. But this is exactly what it is requesting your permission to be able to do, which brings me into the eternal struggle against banking Trojans in the wild. These have been plaguing users since 2011. These have been hosted on the actual official Google Play Store many, many times, so Google's kind of in this constant struggle against banking Trojans to take them off of the Play Store every time they get uploaded, and other many different app stores out there. They've had billions of downloads from the Google Play Store as well, all of these different malware families that have been attacking and plaguing users. There's different prevalent families such as Anubis, Cerberus, Sharkbot, or even the Godfather malware, which we're going to be talking about today. And these actually masquerade as legitimate applications. So that's where the name Trojan comes in. It comes in like Trojan horse. They're going to pretend to be a legitimate application. But on the back end, they're actually doing some shady stuff, trying to probably spy on your device and steal your different passwords, banking credentials, PINs, or anything that it can find and exfiltrate from your device. Now, the origin of the Godfather, this has over 10 million downloads in the official Google Play Store, and it targets over 400 different financial institutions. So that means there's over 400 different banks that the Godfather malware will actually target to try and exfiltrate the passwords or PINs from your device so that it can steal all those funds from all of those different financial institutions. So I'm going to be analyzing a malware sample from 2021 today, but it is still seen in the wild, and there's a ton of different new variants always being released all the time, infecting users. And one interesting fact about the Godfather malware, it was actually derived from the Anubis banking Trojan, which is an older family, and the source code has been leaked online, so if you look on my GitHub, you can actually go through the original malware source code. But this is derived from it so that they could remove all the different antivirus detections and kind of start a new banking Trojan family to infect users. So you might be thinking, if banking Trojans are so prevalent and they've been seen in the wild so much, why are they still effective? Why can't we just block all of them? So what we're going to have to do today is we're going to have to dive into the code and figure out why. Why are they doing this? What are they trying to accomplish? And how come we can't stop them? So the first thing I like to do when installing malware is run it. That's definitely the best choice. So this one, when you install it on the application, it actually has the legitimate looking Google Protect icon. Now, Google Protect is supposed to scan all of the different applications on your device and let you know if you have any malware installed on your device. So kind of ironic here, but that's what the malware author decided to try and pretend to be. And when I kick off this application for my dynamic analysis process, it looks pretty okay here. You can see we have the Google Protect page. And then if you let it load and do its second activity, it says that it's actually scanning all of these different apps on the device, and you can initiate a quote-unquote scan of the device. Now, if you actually look at the resources section of this application, I saw something a little funny when I was preparing for this talk. all of these devices are hard-coded images in the resources section. So it's not actually scanning any of these, it's just putting these images on the screen for the benefit of the user. So that should be kind of one initial indicator that this maybe isn't the real official Google Protect application. But if I continue on my analysis, I see that the application actually stops working. So I'm trying to trigger any potential malicious behavior here so I can decide, is this malware or is it clean? And if it is malware, what is it potentially trying to do to the victim that this is being installed on? So we're going to have to actually take a look at the code to figure out what this is trying to do, since we can't get this behavior to actually be triggered dynamically. Now, the first thing that I like to do if I'm trying to analyze a sample with static analysis, so instead of just running the sample, I'm going to be looking at the code and extracting all of the different components from the compiled application. I'll take a look at the Android manifest, which contains all of the different permissions, components, and classes, and everything defined inside of the application. And this has a few different things going on inside of it. Now, the classes.dex file, dex standing for Dolvik executable, contains all of the actual Java bytecode that's going to be running inside of this application. This one also has a few native binaries stored inside of the assets and lib folder. These native binaries are compiled C or C++ applications that are going to run and execute directly on the underlying processor. So these are all the different components that make up this application. Now, if we take a little bit of a closer look at the Android manifest, we have our activities, which are going to be the things that are in the foreground of the application. And when I first executed this app, that Google Protect activity and then that second scanning activity, those were activities that the user is actually going to interact with. So the user is going to be able to be aware of these and be able to click buttons and do anything like that. So that's not super interesting usually from a malware perspective. But the more interesting code usually lies in services and receivers. Now, services execute in the background, maybe without the knowledge of the actual user running the application. And then receivers will actually wait for a certain event to occur on the device to execute some extra code. Now, this should kind of ping in your brain like, this is actually a really good opportunity for some malware to be stored inside of here. So when we get into the actual code, we might want to check out some of the services and receivers in the application to see if it's doing anything shady in the background that we can't find in the foreground. So let's start. Let's find the entry point of this application in my favorite decompiler, and we'll take a look at some of the code. So I'm going to pull up JDEX. What this is going to do is it's going to take an Android application, and it's actually going to decompile all of the components inside of it. And this, if you're able to see, is my APK file, APK standing for Android package, and this contains all of the executable code as well as the resources and components that comprise this application. So I'm throwing this into JDEX right now, and it's going through, it's taking that dex file, remember that Dolvik executable file, and it's decompiling all that code into Java code that is similar, but not quite as pretty as what the actual malware developer himself coded when they made this application. Now, first things first, I want to actually see what are the components inside of this. So I'm going to go to my resources section, and then my Android manifest that I talked about earlier that had all of the permissions. And if you're an Android developer, this might look really familiar to you, but you're probably used to actually writing this part. But this is what actual reverse engineers like myself or like so many other people out there look at pretty much every day if we're trying to take apart Android applications. Now on top we have all of our permissions, but I'm looking for the actual entry point, so the initial code that's going to execute when I run this application or when a user clicks that icon and actually kicks off the start of this app. So I'm going to go down to my application tag. If this contains a class name in it, this is the application subclass, and this code is going to execute even before the actual main entry point of the app. So what I like to do first is I like to kind of have a sanity check to see if there's any code executing in the application subclass. So I'm going to scroll right, see if there's any class. I'm not really seeing any class name defined here, so I'm just going to move on to the main entry point. And we can find this by looking for the main and launcher tags right here. Now, these intent filters are defining the activity that's going to be the entry point of this application. Now, the actual class name is going to be this com, the next big geek, Squid Game wallpaper, telomit, I can't pronounce that. And that should give you another indication that the malware author actually removed all the original class and method names from this application, and it looks like they just named them random stuff, so sometimes these are kind of funny to look at, but basically what they do is they take out any indication about what these classes are actually made to do. So you don't have the developer names anymore to get an idea. So let's double click on that and see what's going on in here. All right, this contains my actual Java code, so it's not super pretty, but it's going to be pretty close to what the actual developer wrote. And kind of first things first, I notice all of these variable names that just look like junk. So this is definitely obfuscated, and I'll get into what that means in a little bit. So I'm going to go down and take a look at the code. First things first, if you notice, I have all of these methods that are overridden from each other, and it looks like they're doing some mathematical calculations, but they're actually returning void, which doesn't make any sense. Additionally, they're not setting any instance variables or anything like that. So this is actually some junk code or dead code that the developer threw in to try and throw us off the trail, I'm guessing. So basically it pads the top of this class so that if we want to see the actual functionality of this application, we're going to have to keep on scrolling and see what's going on below all of this code. So this goes on for a long time. I'm going to keep on going, and it looks like we've finally gotten to some interesting code. Now we've hit the constructor, and the first thing of interest that I'm seeing here is this string list. To me, this looks like a string of country codes, which I'm guessing it won't run if it sees these certain countries, which is actually really common that we'll see in the wild all the time. So not super interesting to indicate that this is malware, but kind of something to note. I'm going to move on to this onCreate method. Now this is going to be the initial method that's going to be called inside of the Android lifecycle once we actually begin this activity. So it runs after the constructor, but this is going to be the first code that's going to start executing after that. I'm going to keep scrolling down because I see it looks like it's setting up different fonts, TTF files, everything like that. Maybe some GIFs, I don't know. But nothing too interesting, so I'm going to keep on going. And I think I found something of interest here. If you take a look at this is emulator check, this might explain the crash that we were seeing earlier. Now the is emulator check looks like if it is returning true, then nothing's going to happen. Otherwise, it's going to execute all of this remaining code. Now, I was actually, when I first ran this application, running on an x86-based emulator, so I'm guessing that we're seeing the crash because the malware author detected that we were running on an emulator and decided not to run if that was the case. So this seems to me like this is going to be the actual start of our potential malicious code that we weren't able to trigger dynamically when we were running this application. So let's take a quick look at this and see what this is doing. Now I'm going to start with the first code in here. Remember, we've got our junk variable names, but what can we do? So we actually have to look at the code to figure out what this is doing. And I'm going to look at this p-read right here. And this is my function definition for that. Looks like we got some more junk if statements inside of here, but we can ignore that. And this is setting some shared preferences. Now, the shared preferences are often used by Android malware authors to store the dynamic configurations of the device. So maybe if there's certain capabilities on the device, it's going to execute them. But if that device doesn't have those capabilities, it's going to refrain from actually executing that malicious component. And this is kind of similar to ransomware configs, if anybody's familiar with reverse engineering those. But this can also store details about the device that malware authors will commonly use to exfiltrate that data and steal it and upload it to their malicious server so they can look at that later. But that just looks like it's storing some preferences, so I'm going to move on from here. Let's go on to this default variable method. This looks like it's storing a ton of different languages, potentially for the device, or it's defaulting to the language English. So this gives me the indication that it's probably going to be printing some strings to the user. Now remember, we're inside of our malicious code already, so these strings might be really interesting to us because we weren't actually able to trigger them when we were dynamically executing this on an emulator. So I'm going to go into here and see if I can find those strings that are probably going to be printed to the victim. So let's go and see what they're doing. Looks like they're placing the language inside of these brackets, and then they're doing some funky stuff to try and replace that. So let's take a look at this variable and see what strings are inside of here. So this is the declaration of it. So I'm going to press X to get any actual references to it. And let's see where it's getting set. We can see our string getting set right here with a ton of other variables. And I think we've actually found it. We found the really big store of actual string values that get printed to the user. Now, you might think this doesn't look like any string I would print to the user, and you would be right, because this is probably an encoded string that's going to get decoded dynamically while the application is running. So we're going to have to actually go through and decode this. So let's talk about this and go back to our slides. So we found the entry point, and we found potentially malicious code, and we also found some different obfuscation techniques. And this code is actually so difficult to read and so different from what developers would normally write when they're writing Android applications, because it is actually obfuscated. Now, first of all, what is obfuscation? It's kind of a blanket term that everybody uses. It basically just obscures the underlying functionality of the application. So there's a ton of different obfuscation techniques used, such as encryption or packing or so many more. And this is common among all different platforms of malware. It's not just common among Android. This is particularly essential for Android applications because you saw, I could just take the application and throw the app into my favorite decompiler and basically almost see the exact Java source code that the author wrote when they were making this application. So it's a defensive technique to try and protect the actual code from reverse engineers taking a look at it. Now, the obfuscation techniques that we saw for this were some junk code insertions. And those were in the form of those methods that contained those mathematical equations but actually didn't do anything and didn't help the application in any way. And other variants of the Godfather actually have other obfuscation techniques as well. For example, this one has some extra code printed to the screen. Now, if you see this, you might think, my decompiler is trying to communicate with me. It's trying to tell me something in an alien language. But it's actually not. They're just messing around with some Unicode characters in here. And it's really annoying to analyze because it actually takes up the important code on the screen so that you can't read and reverse engineer it as easily. Now let's get back to those strings that we saw at the end of our application. What we actually have to do is we'll have to take a look at the function that is decoding those strings. And if you do, you realize that it's actually just parsing out encoded versions of the strings in multiple different languages. So we can just select the language of our choice and then either create maybe a custom Python script to decode them, or I like to throw them into CyberChef and then call base64 decode, since that was the actual encoding that they were using. And here we go. All we have are our plain text strings now. You can see that this decodes from base64 to phone administrator, which sounds kind of interesting. And if you take a look at all of the different strings inside of that class that we saw that defined so many there, these are going to be the strings of interest that we can actually locate. You can see it's trying to tell you that system files can't be removed. It's checking to see the phone administrator. And it's trying to convince you to enable accessibility for protection to take effect. Now that's kind of interesting, and we'll talk about that more in a second. But we still don't know that this application is malicious for sure. We haven't actually figured out what it's doing. We have no idea at this point. And the actual malicious code, or the code that we think is potentially malicious, is wrapped inside of an anti-emulation check. Now, what these malware authors will do is they'll try to check and see if they're running on an Android emulator, and if that's the case, they'll avoid a lot of their execution. So in this case, the developer has actually caused the application to crash entirely if they detect that they're running on an emulator. Now, emulators are usually based on the x86 architecture, but actual physical Android devices most of the time are based on ARM. So a really common check that malware authors will do is trying to see if the device is running x86, and if it is, then it actually won't execute any of the code. Now, it checks all of these different heuristics and parts of the device to try and see if this is actually an emulator. Here's some other different features that the author here has tried to check to detect whether they were running on an emulator. You can see we have the general x86 check, and they also see if the architecture is unknown, the manufacturer is unknown, or a bunch of different checks as well. And then if more than one of these turns out true, it says this is an emulator and I'm not going to execute. Okay, that's cool, but how do we defeat that? Now, here's our emulator check. We have our isEmulator method that is specified here. This is going to prevent execution of the application. So what we can do is we can use Frida, which is a dynamic hooking framework that works on multiple different platforms, to actually hook this method while it's executing, and then you're able to either augment or completely change the actual functionality of this underlying method while the application is executing. So you can write a completely new method that is not defined anywhere in the app and write it in your own functionality inside your JavaScript that's going to be the hook for this method and have it execute. Now here, our plan is to actually take that isEmulator method, use Frida to hook it, change it so that it always returns false. So even if those heuristics turn out true, we're overriding the actual functionality of this function to change it so that no matter what, it's always going to return false. This should help us actually defeat that check and be able to execute the potentially malicious code that is wrapped inside of this if statement. So let's go on to our next demo. We're going to be using Frida to beat this anti-emulation check. So I'm going to pull up my demo for this. Now let's talk about this a little bit. On the right-hand side, I have my Android emulator, and this is running x86. So this is definitely going to hit the actual emulation check. And then on the left-hand side, I have my custom JavaScript, and this is using Frida to actually override and change the functionality of that isEmulator method, if you can see right here. I'm defining an entirely new implementation for this, and I'm also sending a debug statement to the console so that every time this function is called, it's going to print my debug statement, and then the actual functionality of this is just going to be return false at the end. So let's see what happens. We can open up our application on here. If you look at the center part, we do have the Google Protect, or what it seems like Google Protect, installed on the device already. And now at the bottom, I'm going to start running my actual Frida script. So it's going to trigger that application, and it's going to actually execute that new isEmulator code instead of the original implementation. Now on the bottom, you see we've already got 3 calls to it immediately, right as the application starts. So this is being called in many different locations, so that's why we weren't able to get to the code previously. So let's let this run. This is the actual functionality of this fake Google Protect application. We can see our second activity here. Now one thing to notice, if you look at the emulator right now, it's trying to tell us to enable accessibility services. It's a little bit small, but it's saying you need to enable accessibility for protection to take place for Google Protect. Now that is the string that we found earlier inside of the code that we actually decoded, and this is trying to get you to enable some extra functionality for the application, some extra permissions. So I can go through and enable it there, or in this case, I'm just going to click away. But the malware author really doesn't want me to click away, because even when I do and I try to go to another screen, it just brings me right back here, so I can't get away from it. So like any good malware analyst, I'm going to go through and I'm going to actually give it what it wants, enable accessibility services, and just see what happens. So I'm turning those to on. This is going to let the application observe my actions, retrieve window content, perform gestures on my behalf. I can't see any reason why that would be bad. All right, so I've successfully enabled accessibility services on here, and now looks like absolutely nothing is happening. So that's good, I guess. And if I take a look at the screen, now I see the Google Protect icon is completely gone. So it looks like it's completely uninstalled itself. So many victims at this point would probably think, okay, well that application didn't work. I guess I can just ignore it and go on with my day. All right, so let's go back to our slides and let's talk a little bit. All right, so we did successfully beat the anti-emulation check, and we got more functionality in the application to actually get invoked. Now, we had to do this custom free-to script and hook the emulator method and actually change the functionality. Or it turns out you could have just used an ARM device. So I have a couple different machines running inside of Azure, and one is an ARM-based Azure machine. And I tried using that device, and I didn't even have to do anything with Frida at that point. It just completely ran. So that's kind of sad that it's that easy to get around. But what I want to know now is I want to see, why did this application keep spamming these accessibility requests? It really wanted us to enable accessibility services. Now, what are these accessibility services? They are definitely a legitimate feature for people who have special needs for performing additional functionality, for vision, audio, and mobility needs. And this allows the application to perform extra manipulation of the device, so it can click on your behalf and a ton of different capabilities like that, or it can also parse the content of the page. And it only needs this initial user permission. Once you've given it that permission, though, it doesn't need to ask your permission anymore. It's just able to do this all on your behalf. Now, all different variants of the Godfather actually spam these accessibility requests and try and get you to enable accessibility services. And it's a repeated pop-up on the screen. So if you try and go away from it, go to another application, go to the home screen, go to anywhere, it'll just take you back no matter what you're doing. And it'll keep doing that until you're able to uninstall the application. And some variants of this even have a really annoying alarm sound that'll keep going off until you actually enable those accessibility settings. So that's really irritating to most users. So I'm guessing it seems like they want us to enable accessibility services just a little bit. We're going to have to go into the code, though, and figure out why, because it looks like the application didn't have any other functionality after this. It just looked like it uninstalled itself. So let's go back to JDEX and let's analyze the Godfather module inside of this application. So here we are in our encoded strings section. So put yourself in the shoes. You've been looking at this application for way too long, maybe a few hours, and you're getting tired of it. And you come across an interesting module called the Godfather. So it's kind of spooky sounding too. Now, we're going to look at the input service, because if we search for strings inside of here, we can see it's actually inheriting from the accessibility service, which is going to be defined inside of the Android framework. And this is going to contain all of the code that's handling the approval of those accessibility settings. Now, once the user tries to get rid of those annoying pop-ups and sounds and hits OK, you can have accessibility services on here, this is going to contain the handler code that's actually going to execute what's going to happen in response. So I'm going to scroll down because malware author is trying to fool us once again and insert all of these junk variables and junk methods, but we already know this is just dead code, so we can safely ignore this. So I'm going to keep on going, keep on searching through this application, and I'm looking for a particular method. This is the method I'm looking for, on accessibility event. So as soon as we get those accessibility services, this is going to be the method that actually contains the code that is going to get triggered. Now this is really interesting. Let me scroll this to the left to make sure you can see. Because this is actually parsing the actual page into a node. So the contents of the current page are going to get parsed, all of the different text on the screen, and they're going to be stored inside of this accessibility node info object. So I kind of want to go through and see where this is actually getting used. So I see we have a reference to it down here, our node info object. And it's being passed to this other method and class right here. So I think I'm going to go into that class and see what this is doing with all of that node info. So I'm going to double click. I'm going to go into the method. And it looks like we have another obfuscation technique that the malware author is using. So this could be two things. First of all, maybe the method is just really long and my decompiler actually failed and wasn't able to decompile this method. Or malware authors will really commonly throw additional bytes or anything into this application to try and mess with decompilers and prevent them from successfully decompiling our Delphic executable bytecode back to pretty Java source code. So I can either look at the Smalley code inside of this application. Just to give you a quick example, this is Smalley code. So this is kind of a human-readable assembly-like language that is used for Android applications. But if you're trying to look at this, this is way harder to read than just nice Java source code. So pretty much everybody I know will definitely prefer to read the Java code, if at all possible, rather than the Smalley code, because it exponentially increases your analysis time. So probably at this point, if I wanted to take a closer look at this method, I would try a different decompiler and see if it was successful. But at this point, I'm going to see if anything else inside of this class is actually using this node info. So I'm going to scroll to the right. Oops. Let's see. We have our accessibility node defined right here. Let's see if anything else is looking at this. It looks like we have a lot of other methods inside of this class. This definitely looks like the class that is going to be performing our potential accessibility abuse. So I'm going to keep taking a look. Let's go, let's go, let's go. Looks like it's doing some pattern matching and potentially getting passwords related to this accessibility node info. Let's keep going. And I think we've come to a really interesting portion of the code. I think this is actually explaining what's happening. So we have these different strings that are looking for pin entry, password entry, fixed pin entry, and we even have some regular expressions compiled down here that look like they're trying to detect and see if the actual text is a pin that is inside of the web page. So maybe this is actually trying to parse that web page for passwords. Let's go back to our slides and let's talk about this a little bit. So we finally know why they were trying to abuse these accessibility services so insistently. It's trying to get the contents of the web page, and if it didn't have these extra capabilities, it wouldn't be able to actually get those web page contents for it to parse and try and find passwords inside of our actual page. Now, if we keep on looking at this code, we can figure out exactly what's happening. It's actually checking the foreground application that's currently running on the device, and it's seeing if it's one of those applications in this store of applications that it's going to be targeting. If it is, it creates a new fake HTML web page over top of that application. So this is a fake overlay on top of the actual legitimate application. And then it's actually going to use its accessibility services to be able to parse the contents from the screen and actually trick victims into entering their pins and passwords into the fake overlay rather than the legitimate application. And then it's going to use those regular expressions and patterns inside of the code to try and parse out those pins and passwords from that. Now what this is going to do is it's going to take all of those passwords that it's able to successfully parse from the user, from the victim, who are entering those codes into the application, and it's going to exfiltrate those to a malicious server. Now if you put in and enable accessibility services next time, you might think twice about it because you might find that your bank account is completely drained if you give it those extra services. So for the additional capabilities of this, it's able to post the data to a URL. So it also has an extra encrypted command and control, or C2 server, that is going to take all of the data it's able to exfiltrate from the device and post that to that malicious URL. Additionally, this variant also has capabilities for screen recording. It will go through, record the contents of your screen, and save that to an MP4 file, and then also takes those generated MP4 files and uploads those to the command and control server as well. So this is just kind of like a backup. It's trying to basically steal as much information as possible from the victim at this point to see if there's anything it can get from them. Additionally, it has extra capabilities to be able to execute commands on the underlying device from that C2 server. So these are all of the additional capabilities that this current variant of the Godfather actually has. So it's able to call a phone, so that might give you an indicator of this is why Google Protect was actually trying to request to be able to call a phone on your behalf, because it's not the actual legitimate Google Protect application. So let's go through and summarize some of our findings. We saw all of these different obfuscation techniques used by the Godfather. We saw these meaningless identifiers, so all of those variables, class names, method names actually didn't mean anything. They were just junk inside of the application. And it was also using string encryption, or encoding in this case, to actually try and hide the data from reverse engineers taking a look at the code. And we saw all of those different junk code insertions that we were able to ignore, as well as we bypassed those anti-emulation checks. And additionally, it had some additional native code, native binaries stored inside of this application that gave it ability to connect a remote VNC server. We also had the config with shared preferences, and this actually contains whether it's going to run the keylogger functionality or not if the device is able to handle it. Now, going back to that store of country codes that we saw at the very beginning, if you check the actual functionality of this, it is indeed not executing any of the malicious portions if it figures out that the device belongs to any of these hard-coded defined countries. And remember, I said those services and receivers are really interesting places to look for potentially malicious code. So we had that additional receiver that's awaiting for those accessibility settings so that it can start trying to see what is the foreground of the application, what is the foreground in this current device, should I create a fake overlay over this, and then how can I parse that node info from that fake overlay and get those additional passwords. So let's finish up with just talking about some quick Android banking Trojans in the wild. They target financial institutions. Mostly they target authenticator apps, one-time password generators, and they even started to target cryptocurrency applications. And their common capabilities are to abuse accessibility services, create fake HTML overlays to steal credentials, spy on the device, and listen to SMS messages, and then perform commands from a command and control server, and then intercept those two-factor authentication codes that you might use on your device. So you might be thinking, well, that seems familiar. Didn't we already reverse engineer that? And you will be happy to know we did. So if you're able to reverse engineer this application, you should be able to reverse engineer potentially thousands of different applications that are in the wild, that are infecting users, and trying to steal their banking credentials and drain their actual bank accounts. So now go try reverse engineering some Android banking Trojans, and you should be able to solve this. Thank you, everyone.